Hello, everyone. I just want to finish up a couple of those examples that we missed in today's lecture because I had to run out to that meeting. So at the end of class, I think we had just finished up talking about the medical procedures example and trying to calculate bounds for if this procedure has a 78% success rate and we do 100 of these procedures, trying to figure out upper and lower bounds for the number of patients we expect to see cured based on this particular success rate. So I had one more example when dealing with the binomial distribution. It's a lottery kind of example. So what we're going to do is we're going to buy a lottery ticket each week for the local lottery. Let's assume that we play for the span of the entire year. So here capital N will be equal to 52. And there's going to be a 2% success rate. So there's a 2% chance that we win the local lottery in any given week. So we'd like to calculate the following probabilities. And what I've done is I've copied and pasted this into OneNote so that we have a little bit of space to do this example. And I'll show you how we can think through this example using the binomial function here on the calculator. So I'm just going to get the calculator set up here in the distribution section. And then based on the question, we're either going to select the binomial PD if we want an exact number, or we're going to select the binomial CD if we want a number as well as all of the numbers that are less than it. So let's jot down a few pieces of information. So assuming that we're going to be playing each week, we have N is equal to 52. And we have a 2% success rate. So we know that P is equal to 0.02. So question one is asking, what's the probability that we don't win? Okay, so the probability that we don't win means that we've kind of gone through the full year, so our full 52 weeks, and we're setting X is equal to 0. So if X represents the number of wins, we would like to calculate the probability that we get exactly 0 wins. Okay, so I'm going to pull up the calculator. We're going to kind of hammer through that calculation. This is the binomial PD. So we want an identically equal to 0 kind of thing. So I'm going to choose number 4. I'm going to input our parameters or our variables. So picking number 2, and then just updating this to match with this question. So we want 0 wins. So X is equal to 0. We are going to have 52 trials. We're going to be buying a ticket each week. And then we want the probability of seeing a success to be 2%, right? We win 2% of the time. And bada boom, we get about a 34.97% chance. So 0.3497, or about 34.97% chance that we're not going to win whatsoever. Okay, the second question is, how many tickets do we expect to win over the course of the year? And the keyword here is expectation, right? So that tells me that I should be thinking about the expected value. This is a measure of center. This is a good single number equivalent that's going to give us an idea of what we should expect to see over the course of the year. And the expected value for the binomial distribution is N times P. Okay, so for us, we have 52 attempts, and each of those attempts has a 2% probability of being a success. So multiplying these two numbers together, we should get our expected value. Okay, so I expect to win about 1.04 times over the course of the year. Right? In other words, if I have a 2% success rate, we're really just asking ourselves, what's 2% of 52? It's 1.04. This is our expected number of wins over the course of a year. Okay, our final question, what is the probability that we win more than twice? Now, what I like to do in these particular instances is just draw a rough what's this called? A rough number line to kind of help me think about what numbers I need to input into the binomial CD. So because we're using the words more or less than, I know it has to be the binomial CD function. And I need to be careful because the binomial CD can only answer questions that look like this, right? X is less than or equal to something. And what we have right now is we want more than twice. Okay, so we don't have it in the form that we want. So looking at kind of a visualization, I'm just going to maybe do up to 3, and then I could win, of course, all the way up to 52 times if I'm extremely lucky. And so we're curious about winning more than twice. So this would be success, right? Winning 3 times would be more than twice, 4 times, etc., all the way up to 52. So all of this here in red would be winning more than twice. Or in other words, X is bigger than 2. Now I'm going to come back, and in green, I'm going to put some green dots down here. And these green dots are going to represent winning twice or less. Okay. Okay, and so we could represent that using our random variable as x is less than or equal to 2. And this is the form that is helpful when we go to use the CD function for the binomial distribution. So we can calculate this one that we have in green. Our calculator can do that for us. Let's calculate that probability. So the probability that we win 2 times or less is the following. So let's jump into, we're going to go to our distributions, and then we're going to hit the down button to get into the binomial cumulative. Okay, and we have variables or parameters, and let's input those numbers. So we want 2 times or less, so x is equal to 2. We have 52 trials, and we have a 2% success rate. So 9141, so like 0, 9141. So this probability that we have here is the probability that we win twice or less. But remember, the original question asked us, what's the probability we're going to win more than twice? So in other words, we've calculated the probability of getting, 0 wins, 1 win, or 2 wins. But what we really want is the probability of 3 wins, plus 4 wins, plus 5 wins, all the way up to 52. So the probability that we're going to get more than 2 wins is going to be 100% minus the probability that we get 2 or less. So this is our final calculation. We're going to use that complement property here for probability, and we're going to do a little subtraction here to get our final answer. Okay, doing that, let's see, let's do that subtraction. So 1 minus 0.9141, and let's just double check that gets me, yeah, perfect. So that gets me in the neighborhood of what my notes has, and I have 8.0859, so about 8.59% chance that we are going to win more than twice. All right, so that takes care of the binomial distribution for us. The last thing we want to just kind of quickly discuss is the Poisson distribution, because it was also a part of that last lab as well. So typically, the Poisson and the binomial distributions are fairly similar to each other. We typically tend to use the Poisson distribution in a couple of different cases. Typically, as n gets really big and the probability of success gets pretty small, we tend to favor the Poisson distribution. Or if we're trying to kind of look at the number of successes over some kind of time frame as well, it's possible to use the Poisson distribution here as well. And here is the probability function for our variable. So it has a couple of different parameters in here, and I'm just going to maybe just pop into the slideshow just to kind of highlight some of this stuff. So this is the formula to calculate a probability. We're going to use our calculator to do this. But in case you're curious, it comes kind of jam-packed with a couple of different things. So it comes with this mu, which we've seen before as a kind of measure of center of a normal distribution. So this mu here represents the expected value, essentially, of the Poisson distribution. Or we can think of mu as kind of like the mean of the Poisson distribution. And this letter E is actually Euler's number. And if you wanted to calculate this by hand, you would be forced to utilize the calculator because Euler's number is not a particularly nice number to work with when it comes to inputting things into the calculator. If you would like Euler's number, we use alpha, and we come down here to the times 10 to the x, and that'll get us Euler's number E. So E is around 2.72, and it's just a number that we use as the base for this particular computation. But like I said, you don't really need to know about Euler's number here. What we really want to be able to do is kind of distinguish between, it'll be the same as the binomial, whether or not we want to use the PD function, which is x is identically equal to something, or we want to use the CD function, which is an accumulation. So x is less than or equal to something. So the same kind of thing is going to happen with our Poisson distribution. So when we go to use the calculator, we have two choices. We have the Poisson PD, which is going to evaluate the probability that x is equal to something. And then we have the Poisson. I just really love saying the word Poisson. And yes, it does mean fish. And it was his last name, I think. I believe it was a mathematician's last name. Like, who names their kid? Well, I guess Poisson. Like, where did that last name come from? Like, why would you want your last name to be fish? Anyway, all joking aside here, same structure as the binomial distribution. We have an x is equal to something, that's our PD function, or an x is less than or equal to something, that's our CD function. And what we're going to see when we go to utilize our calculator, just like Microsoft Excel, the calculator is going to need some information in order to do the work. So if we come back here and we look at the formula for f of x, the calculator actually wants us to input x and input mu. So that's what it's going to ask from us. It's going to ask for those two parameters. Now, if usually x is going to be given in the question, mu may not be given in the question, which is why I have the formulas down here for the Poisson distribution. So if mu is not given explicitly in the question, then you can calculate mu by multiplying the number of trials times the probability of success. So we essentially can use the same mean or the same expected value as the binomial distribution if that mu value is not given to us explicitly. Okay, so let me show you kind of what that looks like in our final example here. And so what we're going to do is we're going to do an airline example, because I think this is kind of interesting. So And I want to kind of compare and contrast what we get from the Poisson distribution versus the binomial distribution. So in this particular example, we have an airline. They know that 97% of passengers who buy a ticket to fly are going to show up on time. And the plane that they have has 120 seats. However, they've oversold this flight with 122 tickets. So we're going to try to determine the probability that more people are going to show up than the plane can actually carry. So we're going to try to figure out the probability that 121 people show up or 122 people show up. I'm going to bounce over here into OneNote so that we can start doing a little bit of work. And I'll pull up the calculator too, so you can see what's going to be required from us when we go to utilize the distribution. So if we look at the Poisson, let's look at the CD function. So let's type in 3. And we're usually going to be inputting variables here. We don't usually input a list. So first things first, it's going to ask us for an x value. So I don't know, I'm just going to put something in for now, and then it's going to ask us for the mean, which is mu, okay, or the expected value. And I'm just going to put another number in, and then it's going to spit out the probability. So essentially what I wanted to show you here is what inputs are going to be asked of us when we go to utilize the calculator. So we need to know x, and we need to know the mean mu. Now, this particular case, it's going to be a little bit easier for us to think of a success as a customer not showing up. So if x represents a customer not showing up, then the probability that a customer doesn't show up, or the probability of success, is going to be 1 minus 97%, because we know that 97% of the time the customer will show up. So we're kind of flipping this one on its head a little bit, and we're saying, okay, from the airline's perspective, they actually want some of their customers not to show up. So a success for them would be a customer not showing up, and that happens 3% of the time. Okay, so we've sold 122 tickets, so that represents n. So n is equal to 122, and we have p is equal to 0.03. So now we should be able to figure out mu for the Poisson distribution. So mu for the Poisson distribution is n times p. And that is about 3.66. So on average, we kind of expect about 3.66 people not to show up for this flight. Okay, now let's kind of just draw a little diagram here. We don't need it to be too big. So 0, 1, 2, 3, and maybe number 4. And this will go all the way up to 122. So remember, this x-axis here is going to represent the customers that don't show up. So in red, I'm going to jot down what would be a failure. Or let's see. So if x is equal to 0, that means all customers show up. So if x is equal to 0, that means 0 customers don't show up, or every single customer has shown up. So that would be a failure with regards to the airline, right? So they want to know whether or not this plane is going to be able to fly with the people that have shown up. If all 122 show up, they're kind of done screwed. They're going to probably have to give out some free swag to a couple of these people because they've overbooked the flight. So maybe in red here, we're thinking about this one as everyone shows up. Okay, and that's no good for the airline. Next up, if x is equal to 1, this means one customer does not show up. That means 121 people have shown up, but the plane only has 120 seats. So again, the airline's kind of done screwed themselves up here. This is 121 people show. And that's not good, right? So the plane technically is overbooked in this particular instance. And again, they're going to probably have to give out something free to one individual here. So those, I think, are the two bad cases. As soon as I get to here, then this means 120 people have shown. And this is good, right? From the airline's perspective, this is good. That means they've sold 122 tickets. They're able to fly the plane without having to give away anything extra for free. Okay, and anything after this is going to be good. I mean, maybe eventually you could argue with me that, somewhere over in this neighborhood over here, they may not actually want to fly the plane because they don't have enough people on the plane to make profit. But, if they've sold the tickets, they're probably going to fly the plane anyway because they've already made those profits. So this is what we want to calculate the probability of. This is the probability that... oh no, I apologize. That's not what we want to calculate the probability of. This is the probability that the plane is going to fly and that the correct number of people or less is going to show. So this is good for the airline. What we want to calculate is the probability that more people will show up that can be carried. So we want to calculate the probability here in red. Okay, so in other words, if we would like to use the Poisson distribution, we are going to calculate the probability that x is less than or equal to 1 using our calculator. Okay, so we should be able to do this relatively in a straightforward fashion with the cumulative distribution function. Okay, so I'm going to have to go down into the Poisson CD, which is number 3, and into var. Okay, so we want x to be 1. We want 1 or less people to show. Our mu value, I think we said, was 3.66. And then we hit equal sign, and bada boom, we have our probability that this happens. So there's about 11.99% chance that more people are going to show up that can be carried. So that's an example using the Poisson distribution. I do want to just kind of quickly compare this to the binomial distribution, because in our case, we do have a relatively large n value and a relatively small probability value. And when n is relatively big and p is relatively small, the binomial and Poisson distribution should be fairly close to each other, within maybe a few percentage points. So for the binomial, let's take n is equal to 122, x is equal to 1, and the probability of success is, somebody not showing up. And then we can use the binomial CD function here as well. And like I said, I'm just doing this. We don't need to do this for the question. I'm just doing this as just a little comparison to show you that they're pretty close to each other. So this will be the binomial CD, so number 1 here. Going to input some variables, and we have x is 1, n is 122, and the probability of success is 3%. Okay, so we get 11.61. And so like I said, it's not necessary to do it from a binomial perspective, but you should be able to see that the two numbers that we get, 11.99% and 11.61%, they're pretty close to each other. So sometimes the Poisson distribution is used to estimate the binomial percentages like this if n gets really, really big. Because if n is really, really big, sometimes it takes a little while for the computer to kind of chunk through the formula, and it's a little bit easier for a computer to set up and execute a Poisson calculation, for instance. So there you go. That's going to finish up the distributions chapter. I do recommend kind of reading through the chapters just to kind of solidify some of the stuff that we've been talking about. and definitely try to do a little bit of practice work from these chapters as well, I think. I will try to design questions similar to the ones you've seen in the slides, because I know we did have to kind of motor through the discrete distributions relatively quickly, but I don't think it's unreasonable for the next test to have some questions, some easier style questions from the textbook, or some questions that are very similar to the lab as well. Okay, so with that said, of course, if you do have any questions, just jot them down. Make sure you ask me those next week. And then next week, we're going to get geared up and set up and ready to go for continuous distributions, the first big one being the normal distribution. Alrighty, so I'll see you guys next week.